Hello and welcome to this presentation of the paper entitled Estimation of Multiple Pitches in Stereophonic Mixtures using a Codebook-Based Approach. First, I'm going to give an outline of this talk. First, I'm going to give an introduction along with a small example. Then I'm going to explain the multi-channel signal model that we use before I go into details about the proposed method. Then I will present some experimental results, and finally I will go into a conclusion. So the work presented in this paper is concerned with estimating multiple pitches in stereophonic mixtures. Pitch estimation has applications in many different fields such as separation, enhancement, automatic music transcription, classification, and source localization. So one type of methods is the non-parametric methods, where we, for instance, have the autocorrelation-based methods. Another class of methods are the parametric methods, for instance, the maximum likelihood method. The proposed method belongs to this second class of methods. Often we have music signals that contain multi-pitch signals where harmonics overlap in time and frequency, such as when multiple instruments play together in harmony. It's well known that it's difficult to estimate the fundamentals of such sources. So what we propose is to use a codebook of amplitude vectors that has been trained on individual instruments and employ a multi-channel signal model that takes the panning parameters of the sources into account. So here's a small example. As I mentioned, we might sometimes have the scenario that in music recordings the fundamental frequencies of multiple sources are simply related. In this example here we see the spectrum of a mixture of synthetic sources with fundamental frequency 260 Hz and fundamental frequency 390 Hz. So what will happen in this scenario is that the third harmonic of the first source and the second harmonic of the second source will actually overlap, since they will be located at the same frequencies. If we then use the nonlinear least squares method for estimating the fundamental frequencies, we might obtain this scenario here where the mixture of sources can be modeled as a single source with a more complex model. So we see that in the cost function here the minimum is actually at 130 Hz. So if we were to minimize this cost function here, we would actually get wrong pitch estimates. Now I'm going to present the multi-channel signal model that we use in the paper. So the signal in channel K at time n is modeled as a sum of m sources and noise. So S are the sources, and G and tau are the amplitude panning parameters and delay panning parameters respectively for channel K of the mth source. Each of these sources are assumed to be harmonic, which means that they can be written as a sum of harmonically related complex exponentials where omega 0 m is the fundamental frequency of the mth source, L is a harmonic index, and alpha ml is the complex amplitude of the nth harmonic of the mth source. So the proposed method operates on vectors containing n samples of the observed signal, like this. So this vector of observed signal can be modeled as a sum of m sources, which gives this expression 3 here, where the matrix G contains the panning parameters G and tau. The set matrix contains in the columns these set vectors, which are models of the L harmonics for each of the m sources. This alpha vector here contains the complex amplitudes for the L harmonics. I'm now going to go into detail about the proposed method. So we propose to use the maximum likelihood method for estimating the parameter vector psi, and we obtain the parameter vector estimates by the argument that maximizes the log likelihood of the observed signal given the parameter vector. So for white Gaussian noise, this resembles the NLS method, where we obtain the fundamental frequency estimates as the argument that minimizes this cost function down here. This is a problem that is quite complicated to solve for all fundamental frequencies at once. So one option is to use an iterative approach, such as the harmonic matching pursuit or the expectation maximization algorithm. So the proposed method is based on the harmonic matching pursuit, where a residual is formed for iterations m equals 1 up to the number of sources, where the residual of the current iteration is the residual of the previous iteration minus the model of the most dominant source in the current iteration. Initialization is done using the observed signal, and we use this method for estimating the model parameters iteratively for each source. When estimating the fundamental frequencies of harmonic sources, it is useful to know the model order. We propose to do this using the maximum a posteriori criterion for model selection. The model is found by minimizing this cost function here, where we have a term related to the log likelihood of the observed signal given the model parameters and the candidate model, and another term that is related to the determinant of the Hessian. So this determinant of the Hessian can be approximated using the Fisher information matrix, and we can introduce a normalization matrix K such that in equation 13 the last term is constant and can be ignored, and we can thereby use this first term in equation 13 as the penalty term. We can now state the proposed joint pitch and model order estimator. So the estimate of the fundamental frequency of source M and the number of harmonics for the mth source can be found by minimizing this cost function here, where we have one term which is related to the residual that I previously mentioned, and we have another term here which is related to the penalty term introduced on the previous slide. So we see here that in order to form the residual, we need to estimate the complex amplitudes for source M. So in order to do this, we estimate the vector of complex amplitudes using the least squares method, as shown at the bottom of the slide. Furthermore, we propose to train a codebook C containing k vectors of magnitude amplitudes. And this codebook here is trained using estimates obtained for individual sources, and the codebook is used to restrict the amplitudes of the harmonics by mapping initial amplitude vectors to entries in the codebook. So the mapping is done by minimizing the squared 2 norm of the difference between magnitudes of the initial amplitude vector and the scaled version of magnitude vectors in the codebook. This gamma m here is a scaling factor which is introduced to limit the size of the codebook. In order to use the codebook for varying model orders, we use a variable dimension vector quantization scheme where we use a set of non-square transforms together with the zero padding. The phases of the initial amplitude vectors are then combined with the magnitudes of the codebook to obtain the amplitude estimates of the mth sources, like this. We can then state a refined fundamental frequency estimator, which looks very similar to the previously stated estimator. However, the betas here are calculated in a different way, since the amplitude vectors here are now constructed as in equation 17. I will now present some experimental results. First, let's revisit the example from the beginning of the presentation, where we had a mixture of sources, synthetic sources with fundamental frequencies 260 Hz and 390 Hz. We saw that for the traditional NLS method, if we form the cost function for a number of fundamental frequency candidates and we then minimize this cost function, it would basically result in wrong fundamental frequency estimates. However, if we use the proposed method where we use a codebook of harmonic magnitude amplitudes and the multi-channel signal model, we can obtain something like what's shown here with the dashed line. And if we were to minimize this cost function, it would result in the correct fundamental frequency estimates in this scenario here. We also did some experiments on real signals. And in these experiments, the proposed method was evaluated using some recordings from the Iowa database and the MAPS database for piano recordings. So the codebook was generated by using 10 recordings of anechoic instruments, and specifically different woodwind instruments, playing a succession of notes from C4 to B4. Then the pitch and model order estimates for each frame of the signal were used to form least squares estimates of the amplitudes, and then vectors with the magnitudes of these amplitudes were then used to train the codebook using the k-means clustering algorithm. The mixtures used in the evaluation were created by mixing recordings of 4 notes being played simultaneously. So 2 of the notes were played using a BB trumpet with vibrato, and the 2 other notes were played using a French horn. In total, 8 harmonic mixtures were generated. Also, it should be mentioned here that we assume that the panning parameters are known, but they can be found in different ways, for instance by adding search dimensions to the previously mentioned cost function. So the panning parameters of the trumpet submixture are as follows. So for the first source, the panning direction was 25 degrees, which results in some amplitude panning parameters, while the delay panning parameters were 0 milliseconds for one channel of the first submixture and 18 milliseconds for the second channel of the first submixture. For the horn submixture, the panning angle was 65 degrees, and the delay panning parameters were reverse of those for the first submixture. The pitch estimates were then obtained by performing a grid search, where the lowest fundamental frequency considered is 100 Hz, and the highest fundamental frequency considered is 2000 Hz. And the spacing of this grid here is 1 Hz. So this figure shows the results for one of these mixtures. So the top figure shows a spectrogram, and the bottom figure shows the pitch estimates of this multi-pitch mixture of, as I mentioned, 2 instruments, trumpet and horn, playing the notes C4, E4, G4 and B4 respectively. And we see here that so the circles here denotes what we call the true values, which were estimated using the NLS estimator on the individual signals. The crosses here denote the multi-pitch estimates obtained using the proposed method. So we see there's pretty good correspondence between what we call the true estimates, so the NLS estimates of the individual sources, and the estimates of the proposed method on the multi-pitch mixture. So this slide here shows a table with the results for all the 8 considered mixtures. So the table shows gross error rates for the experiment with the mixtures generated with recordings from the Iowa database. The first column shows the notes and the integer notation. We see here then that in the second column the results of the proposed method, where we have gross error rates. So those are the number of big errors. So in this case, the big errors are errors greater than 1 semitone from the correct fundamental frequency. So the results show that the resulting gross error rate is much lower for the proposed method than for the 2 methods that we compare to. So one method is a state-of-the-art transcription method, while the other is a multi-pitch estimator based on the enhanced summary autocorrelation function. I will now present a conclusion. So in this paper, a method for multi-pitch estimation of stereophonic multi-pitch signals was proposed. In this method, we propose to use a codebook of realistic amplitude vectors, and we also employ a signal model which takes the panning parameters of the submixtures in the mixture into account. Evaluations show that we achieve an increased performance compared to state-of-the-art single-channel, multi-pitch and transcription methods when the proposed multi-channel codebook approach, where the magnitudes of the amplitudes of the harmonic components are restricted according to the codebook. It should, however, be mentioned that we also performed a small-scale experiment on the MAPS database, which actually showed preferable performance for the BW 2015 method. However, we suspect that this is due to the fact that the proposed method is based on a harmonic signal model, and since the MAPS database contains recordings of piano signals, this harmonic model is actually not fully satisfied. Furthermore, it should be mentioned that the proposed method outputs continuous pitch as opposed to transcription methods, where the output is sort of resembles a piano roll. And it should also be mentioned that from this method that we propose, it's possible to obtain a full parameterization of the signals. So in fact, it can be used for a kind of implicit separation of the sources. And in the future, it would be interesting to look into how to incorporate a detection scheme such that the number of sources is not needed a priori. Furthermore, it would be interesting to look into how to estimate the panning parameters and maybe exploit that in such submixtures that we have investigated. Often the panning parameters are constant for longer periods of time. That's all, and thank you for your attention. I will just show the two final slides here, which contains the references used throughout the slides.